So we are looking at tax 1, which talks about the majority talk about the set builder notation. So when you look at the question I, it said a string over all the alphabet, which is equal to 0, 1, and 2. That begins with 1 and 2. That means that in all the string of the alphabet can be we are going to look for the language that the machine speaks, and the string which is the alphabet, which is 0, 1, start with 1 and 2. That means it can be anything which is 1, 2, 0, 1, 2, 2, 0. Just note that it has to start with 1 and 2. So looking at it, we found the language which L is equal to W is a member of all the alphabets, such that W is equal to 12x, because all the string have to start with 1 and 2 for the same x is a member of all the alphabets star. So this is the language that we found for the set builder notation, which is I. Then when you look at the II, a string over the alphabet A, B up to Z that contain at least one A and B. So that one too, you are going to find the language. And finding the language, you just have to know that the II, you know that with the alphabet it begins, you have to find from the arbitral prefix x and then the suffix y. So to find that, you have to first, so finding it, you have to break it down to x plus ab plus y. And when you break it down to that, just you have to make sure that ab have to appear somewhere. Hence breaking it down, because ab have to appear somewhere, finding the language become L is equal to x star ab star y, such that x, y is a member of all the alphabet star. I hope you are getting it. So even looking at it, you can see that we've even given an example that the substring AB occurs somewhere between the arbitral prefix x and the arbitral suffix y. That can further help you to understand how we got that language. So when you come to the I say the string over the alphabet THE that have only one copy of THE. With this one too, you have to break it down to make sure that THE will definitely appear somewhere, like the one we did in II. So you can get the substring THE occur somewhere between the arbitral prefix T and then the arbitral prefix E. So with arbitral there's no substring of x and d. It's not substring of y. This focus exactly one occurrence of the exact condition on x and y rule out of 0 or greater than or equal to 2 occurrence. So looking at it, you realize that it's similar to the one we did in II. So hence you get the language this. So with the IV, the set of positive odd integers. So you can also see that we are going to look for the language of a set of positive odd integers, which ends the language n is a member of, this is the sign of integers. That's the sign of integers, then plus. So with this one, you can see that 0 is not part, and such that n mod 2 is equal to 1. So written as a language of Dickie string, no leading zeros. Like I said, positive odd integers. So you can see that the language is W is a member of 0, 1 up to 9 star, such that W has no leading zero, and the last symbol of W is a member of this, like I was saying. So be DFA over the alphabet X and Y. So the string that ends in X and Y. DFA diagram is already explained in a way that you understand. So we have the Q0, Q1, and Q2. Now the arrows are showing where it returns and where it goes back to. So DFA accepting string ending in XY as Q0 start, Q2 final. So when you look at the Q2, it has two circles, which is the accepting state, that's the final state. So the Q2 has the final state, and the starting state is initiated by the Q0, which is 0. You can see the diagram can easily explain itself, and then the table also can tell you how it is formed and how it accepts from Q0, how it goes back to Q1, then test in Q2 whether it accepts before it comes back to Q0 again. So you can see that it is all explaining itself. So when it's Q0, X becomes Q1, and the accepting stage is Q0. So you can see everything. So everything that was shown here is drawn exactly like that from the answer that we give from the set notation. So we'll do a next video for task 2.